We continue our discussion of character encodings. We've seen fixed length encoding, variable length encoding, and some practical examples. Now, I want to point out that in general, you have to be a little careful with these being the variable length codes, because you can get into trouble. And what the trouble looks like is shown on this example. So there's an innocent looking encoding for a small alphabet here. You have a code word for each of the letters, all fine. So you can encode something, for example, the string banana would correspond to this bit string. The problem then shows up with decoding. You can take the same bit string and decode it to an entirely different source text. That's not exactly what we wanted. We wanted lossless compression, so we should always be able to get back the precise source text we put in. If you just look at this code, at the set of code words, without thinking about deeply, this looks fine, right? They're all different, so where's the problem? In this case, the problem simply is you can decode some coded texts in multiple ways. That is the core problem. That's what we really don't like. And in general, you can think about how you can recognize if a given set of code words has this property. We'll focus on a simple sufficient condition. So a condition that's easy to check. And if that condition's fulfilled, the code is fine. But there may be other codes that are still working fine if you look very close that do not satisfy that condition. I just want to make that clear. So you can design some more complicated things, and they might still work, but we'll exclude those.
Something I was thinking about, like, so for stuff like this, can't you just like, let's say you have like the source domain, and then the like. So we have like the domain, which like the set of strings, the set of string of length. Let's say like compressing from like length all strings or string of a particular length. So we could like group all strings of that length that are like semantically equivalent or roughly equivalent, that have like the same semantic content for whatever our purposes are. And those strings that have the same content can be overlapped when we compress it. So we are compressing those strings to a string of a smaller length, then all strings have like the same content, the same semantic content or semantic meaning, or like.
Well, okay, let's. What we want in this chapter is just a string, and there's no semantic behind it. If it's two different strings, they're different. And so I don't want to combine them in that way. Now, sometimes that makes sense, but then again, I would say you're just shifting the problem. You're saying, I'm actually encoding something else, namely the equivalence classes over strings.
Yeah.
And maybe I don't have yet a convenient way to write them down as a single string, but there may be one lurking in the background. Let me make some progress on the material here that you can do the tutorials and the last class test after today, ideally. After today, when we cover, I don't want to release a class test that has material we haven't covered, because then I can already see the 10 emails. Hey, I don't know what to do on this. Yeah, of course, we haven't talked about it. So I'll release it once we have covered all that's needed. Probably the latest is to move to front. So we might just not make it today. Maybe you have to wait till Monday. So here's the simple condition I promised that lets you easily decide if such a collection of code words is valid. And that's if they're prefix free. Same condition we had for tries before. So the problem in this code can be seen as there's one code word, this one, that's a prefix of another one, not including the second zero. And so when you see 100, you're not quite sure at this point if it's an S or if it's a B and it's the beginning of something else. If we forbid that, we definitely don't have this problem. If we always have a code word that's not a prefix of something else, as soon as I've finished reading a code word, I can decide this is decodable and I can move on. I will never ever get in some dead ends. So if we have a prefix-free code, then it is instantaneously decodable. What that means is what I just said. You read the code word, and you can immediately decide that is this letter, and there's no backtracking needed of some sort. And that implies that the code is uniquely decodable. There are other uniquely decodable codes, but we won't care about them. Another convenient consequence of being prefix-free is, as I alluded to, we can represent these code words as a trie. And that will be convenient for two ways. One is you can just draw the trie of all the code words to check if they're prefix-free. If you end up with something in the middle of an internal node or inside of an edge, it's not prefix-free. And the other reason why the code trie is convenient is for decoding, you need exactly such a representation. So let's do a different example. This is a code that is prefix-free. And here's the code trie for that. So you can follow any path down. You never stop in an internal node. You always continue to leave, and then you find uniquely which letter that code word corresponds to. Well, here's an example down here for encoding. It's not so interesting. For encoding, you really want this table where you can look up quickly for each character what is the code word. So A should be 0, 1, and then N should be 0, 0, 1, and so on, right? You just concatenate all the code words. And so here's what that looks like. And for the decoding, should put this on two separate slides. For the decoding, it's really much more convenient to work on the trie. So you start at the root of the trie and start at the beginning of your coded word. And now you just read along. I read a 1 and I read another 1, and then I'm at the leaf level. So I know the first two 1s correspond to a T. Then I'm done with one letter and I start at the root again, do the same game over. Start at the root, you read a 1, then I read a 0 and another 0. So I reach 1, 0, 0, and that's an O. And so on and so forth. So 0, 0, 0, the next three letters lead us to the space. And 1, 0, 1 gives us an E. Okay, we might as well finish the 2. And then 1, 1 was T. Okay, and here's the nicely typed version. So again, two things are convenient about prefix-free. It's always uniquely decodable. You can draw the code trie to check, and you can use the code trie to decode conveniently. And the table of code words is for encoding. Now, once we've talked about various codes, in particular these ones, which are something I just made up for the example, the question upon decoding is, how do I know which code to use? And there's many options. I mean, what we're often used so far was a fixed code, like the ASCII code. It's a standard, so that means outside of your specific application, someone decided this is the code that we'll use, and then everyone knows what to do, hopefully. And the same for Morse code, although there were different variants, as I mentioned. That's one option. A fixed coding means you somehow externally know which code to use. Static coding is a subset, is a generalization of that. Fixed coding is also static, but static means the code could be part of the message. So the first part of the message tells you what code to use, and then the remainder of the message is decoded using that code. So in a way, you have to decode the decoder first. And we'll see an example in terms of Huffman codes for that. There's also the option that there's no fixed code that stays the same, but instead the code keeps changing while you decode. That sounds confusing and wild, but you'll see an example later. It's just an algorithm that implicitly constructs a code as you keep going. As long as encoder and decoder do the same thing and at the same position in the text have the same code in mind, it works fine. right? It's not a problem that the code keeps changing, as long as at any point in time you know what to do, and it's the same what the encoder has done.